Hi there, this is Chris, and this screencast is going to be the replacement for the lecture that would have happened on Martin Luther King Day. So you can watch this screencast. Alternatively, you can actually read the Bits and Bytes chapter in the course reader, and it covers the exact same information. And if you don't want to sit through this screencast, then you are welcome to read that, and I think you will probably get just the same exact information, and you don't have to sit here and listen to me talk. So let's jump right in, and we will start. First, a couple of logistics. Assignment 0 is actually due Monday night on the holiday, unfortunately. The next assignment is going to come out on Tuesday, which is your first real assignment, I would say. It's the first assignment that's going to be covering material we covered in class through this lecture. And labs actually start on Tuesday, and you will definitely want to understand the material for this lecture before you get to lab. And not quite as much for lab, but actually for the assignment, you absolutely will have to understand this material. So, as I said, the things we're going to cover today are going to be in the Bits and Bytes chapter of the course reader. It's also in the textbook chapter 2.2. Now, the textbook chapter is pretty mathy. With regard to the details of some of this stuff, particularly the things that we covered actually in the last class, but it's also very good. So I would suggest at very least looking at the chapter, but I've tried to cover it all in the Bits and Bytes chapter in the reader as well. So that's that. All right, so today we are actually going to we're going to continue talking about integer representations. Now, we did that in the last lecture. We kind of set the whole process up. I'm going to kind of go through that briefly again, and then we're going to see how numbers are actually represented both in signed and unsigned format in the inside the computer. All right, then we're going to talk about casting and how casting works in the computer, in C in particular. And then we're going to talk about comparisons. Comparisons are actually an interesting part of C. You have to be very particular about how you recognize how comparisons are done. And we're also going to talk about a couple other things like the size of operator, which tells you how big particular data types are. And we're going to talk about the min and max of some various integers, and what happens when we actually convert integers from one type to another. In particular, how we convert from bigger values to smaller values and what happens in that truncation phase. All right, and then we're going to talk about what we call 2's complement overflow. 2's complement is how we store signed numbers, and we'll get into the details of that as we go along. Okay, so let's get going. Integer representations. Here's where we left off the other day. This is kind of a bit of a review. The C language has two ways of representing numbers, unsigned and signed, and C is interesting in that it's one of the few languages that has unsigned integers. Most languages just don't worry about the unsigned and just deal with signed integers. It's kind of nice in that respect when you don't have to worry about the differences, but C is not one of those languages. So we're going to talk about how this computer represents both. Okay, so we've talked about binary numbers, we've talked about representing binary and decimal and doing the conversions. When we talk about unsigned integers, an unsigned integer does not have negatives, only goes from 0 all the way up to 2 to the width minus 1. In other words, if you have 32 bits, for instance, in your number, okay, you can represent between 0 all the way up to 2 raised to the 32 power minus 1. All right, that's the range that we have. Okay, so let's take an example of a 4-bit number. So if we only had a 4-bit number, okay, we could represent 0, 0, 0, 0. We could represent 0, 0, 0, 1, which would be 1. We could represent 0, 0, 1, 0, which is 2, and 0, 0, 1, 1, which is 3, all the way up to 1, 1, 1, 1, which is actually 15. Okay? So you could represent all the way up to, from 0 all the way up to 15, which is, because there's 4 bits, that's 0 up to 2 to the 4, which is 16, minus 1. So you can represent between 0 and 15. That's how unsigned numbers actually work. Okay? For 32-bit numbers, okay, for 32-bit integers, we can represent between 0 to 2 to the 32 minus 1, which is up to a bit over 4 billion numbers. Okay? So that's how unsigned integers work. Actually, unsigned integers in some sense are the easier of the types of numbers to deal with. Okay? All right. So now we go into signed integers. And this is where we kind of did the last couple minutes of class last time on this. What if we want to represent negative numbers? Well, we have to figure out how to do that in a binary notation. Now, in regular old mathematics, we just put a minus sign in front of the number. So if we want to represent minus 12, it would be minus 12, right? If we wanted to represent minus 3 in binary, we could say 3 is 0, 0, 1, 1, and only 4-bit, let's say. And then we could say minus 0, 0, 1, 1. But the problem is the minus, there is no minus digit, right? So this is like a language issue here. We've got the minus represents the negative in this case, but we don't have that. So we have to use ones or zeros to do this representation. Okay, so what we can do is we can say, all right, let's say that we have a sign bit. And a sign bit is simply one bit that we pick, the first bit in particular, and the most significant bit, as it turns out, and we say, look, a 0 means negative, or a positive, and a 1 means negative. Okay? So we could represent our numbers like this. We could say 1 is just going to be 0 for positive, and then 0, 0, 1, and that means 1. And then let's say 6, which is 1, 1, 0, positive 6 is a 0, 1, 1, 0. Now that's one way to do it. And then if we do the negative equivalence, we could say, all right, look, here's 1 meaning negative, and then 0, 0, 1 is 1, so that's negative 1. And then negative 2 would be 1, 0, 1, 0, etc. All right? All the way down to 1 for negative, and then 1, 1, 1, which is negative 7. Now, this is fine, except for the fact that if you count the numbers here and the numbers here, we only have 14 possible combinations. So, but remember, we can actually represent up to 16 numbers. In unsigned, we would have done 0 through 15, which represents 16 numbers. But now we're going to go negative something to positive something. And right now, in our format here, we've only represented 14 of those. We've got 2 extra numbers. And of course, those numbers are simply like 0, right? We haven't represented 0 anywhere in here. Okay, and we've actually got 2 possibilities. We could say, well, here's 0, 0, 0, 0, and 1, 0, 0, 0, and this would really mean positive 0, and this would mean negative 0, and that doesn't really, it kind of makes sense mathematically. You can talk about positive and negative asymptotes approaching 0 from one direction or another, and it works out nicely in that sense, but we don't really like that. We want one representation of 0, and, well, that actually, because we're really only going to use one representation of 0, this would not be a particularly efficient way of doing things. Okay, so what we do actually is we say, well, maybe there's a better way to do this. Okay, we only want one representation of 0. We still want to use a signed bit, but what can we do? Okay, well, as it turns out, our choices, okay, are that we refigure out how to represent the negative numbers. Okay, so if we make 0, 0, 0, 0 equal to 0, which kind of makes sense. You kind of want all the bits, if all the bits are 0, you want that number to represent 0, right? We could do that, and then addition is relatively easy, although the problems are that doing subtraction is not particularly easy, or even addition of a negative and a positive number, not really tricky, because when you try to do 5 plus negative 4, what are you really doing? You're really saying, you're really saying, well, this is actually 5 minus 4, and you have to do the subtraction, and you have to figure out how you're going to deal with subtraction and so forth, and it's not particularly easy. Well, it turns out there's a better way, okay, than just this simple representation of saying the sign bit is determines whether it's negative or positive, and then the rest of it is just the binary equivalent of the number if you converted it from decimal to binary. Okay, so we're going to talk about that better way. All right, as it turns out, we actually have a representation which was developed in the early days of computing. One of the giants of computing named John von Neumann actually suggested this in 1945. And what it is this thing called 2's complement representation. Now, what this means, it turns out it's actually a very efficient and beautiful, in many ways, notation. And it just takes a little bit of figuring out how to what it actually means in the bigger picture. Okay, so let's think about what this actually is. What I've got here is what we call a 2's complement circle. This circle here is what we call a 2's complement circle. Now notice what's going on here. We represent the numbers 0 through 7 on the right-hand side of this, and those are just the binary representations, just like we always have talked about them so far. Okay, 0, 0, 0, 0. And by the way, this is for a 4-bit number. This expands to any width numbers, but the 4-bit's the easiest to see and the most easy to see directly. So we've got 0, 0, 0, 0 for 0, 0, 0, 0, 1 for 1, 0, 0, 1, 0 for 2, 0, 0, 1, 1 for 3, etc., all the way up to 7, which is our normal 7, 0, 1, 1, 1. Okay? Now, what happens after this is we actually go into what we call this 2's complement notation, where negative numbers still have the first bit being the sign bit. In other words, if you see the first most significant bit is a 1, you know it's a negative number. Okay, so that's the first thing. Okay, and the second thing is that after you get to 7 here, the next number up, 1, 0, 0, 0, is not negative 1, it's actually negative 8. Here's where the dividing line, well, the dividing line is between negatives and positives is here, but as you, the way it works is kind of like a number line, in that if you go this way from 0, you get the positive numbers. If you go this way from 0, you get the negative numbers. Okay, but the numbers actually continually go around in the circle like this. Now, the question is, why do we do this, and B, like, where does it actually come from? Well, this 2's complement notation is just a representation of the numbers such that the width of each bit is still a power of 2, just like it's always been, okay, except the most significant bit is the negative power of 2. In other words, it's not going to be just, it's not going to be the, like if we have a number 1, 0, 0, 1, this is normally 1 times 2 to the power of 0 plus 0 times 2 to the power of 1 times, or plus 0 times 2 to the power of 2 plus, it would, normally in unsigned it would be 1 times 2 to the power of 3, but now it's going to be 1 times negative 2 to the power of 3, and we add this all up. Okay, so 1, 0, 0, 1, for instance. Okay, let's look at this. Negative 2 to the power of 3. Well, 2 to the power of 3 is 8, so negative 8, right, plus 0 plus 0 plus 1 is actually negative 7. And if you look over here, 1, 0, 0, 1 is negative 7. Okay, so this is actually how it's like the definition of this. Now, how do you actually do these conversions? Well, it's actually pretty easy. There's a couple different ways. I'm going to show you 2 different ways. A negative number is obtained by inverting all the bits and then adding 1. Okay, just inverting all the bits is actually called the ones complement, but we're going to talk about the twos complement, which is invert all the bits and then add 1. Okay, so let's see an example of this. Let's take 5. 0, 1, 0, 1. And by the way, you have to know how big the number is in order to invert all the bits. In this case, we're dealing with just 4-bit numbers. Okay, we have 4-bit numbers here. And what we've got in this case is 0, 1, 0, 1. Okay, so what do? You invert all the bits. We're converting positive 5 to negative 5 in 2's complement. All right, we're going to invert all the bits. 1, 0, 1, 0. Okay, 1, 0, 1, 0, that's inverting all the bits. This is the ones complement notation here. And then we add 1. Okay, so we're going to add 1 to this number. And 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 0 is... Yeah, by the way, we're only adding these two numbers here. This number, 1, 0, 1, 0, and the 1. Okay, and then 1 plus 0 is 1. So we get 1, 0, 1, 1. And this is negative 5 in 2's complement notation. Okay, and if you notice, 1, 0, 1, 1 over here is negative 5. All right, let's try another one just to kind of get used to this. Let's turn 2 into negative 2. Okay, 0, 0, 1, 0 is 2. That's positive 2. Okay, how do you do this? You invert all the bits, 1, 1, 0, 1, and then you add 1. Okay, and then we add 1 to that number, just these two bottom numbers. We're adding 1 to this. Okay, 1 plus 1, well, it's actually 1, 0, so we actually have a carry here. And we have 1, 1, 0, and then there's a 1 up here. 1 plus 0 is 1, and then 1 plus 0 is 1, and 1 plus 0 is 1, and we get 1, 1, 1, 0, and you'll notice over here 1, 1, 1, 0 is negative 2. Okay, so that's how you do the conversion. I like to show people a slightly faster way to do the conversion, which doesn't involve this adding 1 business. It's actually, I like to do it, I learned this when I was an electrical engineering student, and here's how it goes. If you want to convert 0, 0, 1, 0 into, actually I think this is on the next, let's see, this is the one we just did, and then here's the trick. If you want to convert 0, 0, 1, 0, okay, to in fact I've got the example exactly right here, to a 2's complement representation, to its negative 2's complement representation, what you do is you go from the right and you start writing down numbers until you hit a 1 and you write that down. So we've got 0, 1. So we write down the 0, write down the 1, and then you flip all the other bits. And that's it. So it's actually a little bit quicker, I think, to do this. So we'd go 0, so if we have 0, 1, 0, 0, and we want to do this, we write down the 0, write down the 1, and we go, aha, we hit a 1, flip all the other bits. 0, 1, and then 0, 1, and then flip all the other bits, which were zeros, 1, 0, and that's the 2's complement notation. Okay, so that I think is actually a quicker way of doing it. Let's try the other. Oh, by the way, it goes in reverse too. If we want to convert negative 5, let's say 1, 0, 1, 1 to, that's negative 5. If we want to convert that to its 2's complement notation, the tricky way is to go, okay, write down numbers until you hit it. Well, we hit a 1 and then flip all the other ones. 0, 1, 0, and 0, 1, 0, 1 happens to be positive 5. Okay, let's actually do that because I didn't show you that example before. Let's actually convert negative 5 to positive 5 using the regular way we would do it before. Negative 5 is 1, 0, 1, 1. Okay, that's negative 5. And if we want to convert that to positive 5, the regular way of doing this is invert all the bits, 0, 1, 0, 0, and then add 1 to that. Okay, and then we get 1, 0, 1, 0. 0, 1, 0, 1 is positive 5. Okay, that is not slow, it's just that's the more explicit way of doing it. I tend to use the trick when I'm trying to really quickly convert from negative to positive. Now, a note on what we're actually calling these things. 2's complement notation is this number is in 2's complement notation, and it is positive 2 in 2's complement notation for a 4-bit number. This is the 2's complement notation for negative 2. Okay, same thing for the other ones on here. We sometimes talk about converting to 2's complement, but it really means converting to the negative or the positive. Okay, so the 2's complement notation is 0, 0, 1, 0, etc. Okay, and 1, 1, 1, 0. But sometimes we say, well, let's perform a 2's complement conversion. The 2's complement conversion part is this adding, or flipping all the bits and adding 1, or doing this trick. So that's how 2's complement works. Now, why do we bother doing this? Well, first of all, notice something. In this form, okay, we only have 1 0. It's not 2 zeros. We can represent numbers from 0 to positive 7, and then the other direction, 0 to negative 8. As it turns out, the negative 8 comes from the fact that there's this one overlap. We've only got 1 0 now. We can represent 16 numbers, meaning there's 15 non-zero numbers we can represent. And it turns out that the extra 1 happens to be the lowest negative number. So you can go all the way down to negative 8, but you can only go up to positive 7. Okay, so by the way, some people say, well, what if you try to do the conversion on negative 8? Well, let's try that. 1, 0, 0, 0. Right? Invert all the bits, you get 0, 1, 1, 1. And what happens if you add 1? Well, you get 1 plus 1 is 0, and then 1 plus 1 is 0, and 1 plus 1 is 0, and then 1 plus 0 is 1. You get back 1, 0, 0, 0. So there is no positive 8 in 4-bit 2's complement notation. Okay? The 1, 0, 0, 0 means it's negative 8. Okay? So anyway, the point is that it's nice that we have the 1, 0 now, and we can represent 16 numbers, and there's a nice notation. I mean, it goes negative 8 all the way to positive 7. Okay, negative 8 all the way to positive 7. And that's how we can think about it. All right, that is not the only interesting thing about this, as it turns out. Okay, I already did the more complement notations. Again, converting negative to positive, just do the same thing. Okay, so as I said, 1, 0, great. The highest order bit is 1 for negatives and 0 for positives. That's good. It means we can look at the highest order bit and tell whether the number is negative or positive. What's really cool about this is, remember how before I said that adding a positive and a negative number, you have to actually do the subtraction, and that, you have to know how to subtract versus just add. Turns out you don't have to know anything other than addition to add two numbers together. Okay, so what does that mean? Well, let's take a look at this. If we add 2 plus negative 5, okay, that's negative 3. How do we do that? Well, we write down 2, 0, 0, 1, 0, that's 2. We write down negative 5, 1, 0, 1, 1, and we just add them. Okay, I'll actually do it explicitly over here. 0, 0, 1, 0 plus 1, 0, 1, 1. This is negative 2, and this is positive 2, and this is negative 5. Okay, let's just add them. 0 plus 1 is 1. 1 plus 1 is 0, with a carry. 1 plus 0 is 1, and 0 plus 1 is 1. And guess what? 1, 1, 0, 1 is negative 3. Okay, 1, 1, 0, 1 is negative 3. You don't have to do any subtraction to add 2's complement numbers. Really cool property. Okay, this is a very cool property. If you want to do subtraction, you do the 2's complement conversion and then add. So when we build computers, we only need to teach them how to add if we're using 2's complement notation. We never need to teach them how to subtract. We just use this notation, and then everything actually works out. Okay, and you'll say to yourself, well, what happens if you actually end up going too high? Like, what if we add 5 plus 6? Well, we'll see what happens there, but that's actually an overflow condition, because 5 plus 6, which is 11, right, is not represented in our 4-bit circle here. It's not even represented at all. Okay. All right. So addition is just adding. Well, that's pretty cool. Okay. Subtracting, as I said, perform the 2's complement and then add. So if we want to do 4 minus 5, right, we say 4. It's down here, but I'll do it explicitly. We say 4, right, 1, 0, 0, that's 4. And then we just say, all right, fine, let's add negative 5. right, plus negative 5, and we can do the conversion for negative 5, and we know that's 1, 0, 1, 1, 1, 0, 1, 1. And if we add these, we just get 1 and 1 and 1, and 0 plus 1 is 1 as well, and that happens to be negative 1. Okay, so this is negative 5, and now we're just adding, and we get negative 1. Okay, by the way, all 1s in 2's complement notation is negative 1, no matter how many bits you have. Okay, no matter how many bits you have, all 1s is negative 1. Okay, so that's another cool property. Adding's easy. Subtracting is also easy if you know how to do the conversion to the opposite sign, and then you just add. Another one, multiplication, also works perfectly, which is actually really neat. Now, what you have to worry about is whether or not your numbers fit into the number of bits that you have. So in this case, I've chosen negative 2 times negative 3, and that actually gives you 6, which fits 6 we can represent. If you try to do negative 5, let's say, times negative 4, well, that's 20, but that doesn't even fit in your 4 bits. Okay, so you can't do that. So let's actually do this. I've got it right out here. You say 1, 1, 1, 0, which is negative 2, and 1, 1, 0, 1. Here's negative 2, and here's negative 3. And you multiply them. Well, to do multiplication, it's exactly like you normally would do. You'd say, okay, well, 1 times 0, or rather, 1 times 1, 1, 1, 0 is 1, 1, 1, 0. 0 times 1, 1, 1, 0 is 0, 0, 0, 0. 1, 1, 1, 1, 0. It's actually not too bad. You're always doing either this number or 0. And then when you line everything up, and then add, you get 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 0 plus 0 is 1, 1 plus 0 plus 1 plus 0 is actually 0 with a carry of 1, 1 plus 0 plus 1 plus 1 is 1, and that carries, and then 1 plus 1 plus 1 is 1 with another carry, and 1 plus 1 is 0 with a carry of 1. The 4 bits that are the lowest bits out of this are the ones that remain, and that gives you your answer. You just cross off any other bits that don't remain. So what's nice is if you teach your computer how to multiply, which is not a bad thing to do, you can teach the computer how to multiply, and you can just simply multiply, not worrying about the sign at all. You don't have to worry about this as negative 2 and negative 3. Right? You don't have to do anything. Oh, if they're both the same sign, it's going to be positive. If one's negative and one's positive, it's negative. You don't even worry about that. It just works out. So that's another very cool property of 2's complement notation. Okay. So those are the big useful properties, and in fact, they're very useful in the sense that now that we have this format, we can do arithmetic very quickly with very few operations, as it turns out. So those are the reasons we use 2's complement. 1, 0. The numbers are a nice little number line format here. Negative 8 all the way up to positive 7 in the terms of in 4-bit notation. And addition is easy, and subtraction is also easy, and multiplication is easy. So those are the big ones, the big reasons that we use these powers. Okay. Again, remember, it's still just powers of 2. That last power of 2, that highest order power of 2, is just the negative of the power of 2. Okay? So again, I already did this example before. Negative 5 is 1 times negative 2 to the power of 3, because there's a 1 in that case, plus 0 times 2 to the 2, plus 1 times 2 to the 1, plus 1 times 2 to the 1, and that actually is 8 plus 0 plus 2, or rather negative 8, plus 2 plus 1, which gives you negative 5. Okay? Just remember that when you're trying to figure out how this actually works. And this is notation from the book, by the way. Okay? They talk about the explicit way of doing this. All right. Now that we kind of have an idea of how 2's complement numbers work, okay, let's actually do a little practice on these. Okay, let's actually convert the following numbers from positive to negative or from negative to positive. All right, the explicit way to do this is to say, okay, invert all the bits, 0, 0, 1, 1, and then add 1, and you get 0, 1, you get 0, 1, you get 1, 0, and you get 0, 1, like that, and the answer is 0, 1, 0, 0. I think that's it. There we go. And the tricky way to do this, the quicker way to do this, I would say, is just go write down all bits until you get to a 1, 0, 0, 1, and then flip everything else. Done. All right, let's use a tricky way to do 7 to negative 7. Write down a 1 because you hit the 1 and then flip everything else. 0, 0, 1. 1, 0, 0, 1 is negative 7. Okay, the explicit way is say, okay, flip all the bits, 1, 0, 0, 0, flipping all the bits there, and then adding 1. 1, 0, 0, 1 is our negative 7. Okay, it's actually not too much slower to do it that way. It's just the other way is maybe a little bit faster. Okay, 3 is going to be 0, 0, 1, 1, so we're going to go write down the 1 and then flip everything else. 0, 1, 1, 1, 1, 0, 1 is negative 3. And then we already said negative 8 is that interesting one where we say, okay, well, let's do this. Let's go down and write all the numbers until we get to a 1, and then, oh, we're done. So that's that. Or you can do the practice we did before where you flip all the bits and add 1, and you end up getting back 1, 0, 0, 0. Okay, so that's the practice with those. Okay, remember, no positive 8 in 4-bit 2's complement notation. Okay, if we had 8-bit numbers, the math is the same. It doesn't represent. It's not represented in the chart over here because there's actually 2 to the 8th minus 1, which is 256. Basically, 256 different numbers in 8-bit. We go negative 128 to positive 127. That's the range. Okay, this is actually the signed char range in C. Okay, what's the easiest way to do this? 0, 0, 1, flip all the others. 0, 0, 0, 0, 0. That's 4. And by the way, look, it is 4. 0, 1, 0, 0 is just 4. Okay, how about 27? If we want to convert 27 here, let's do that. I'll do it the fast way. Go from the right until you hit a 1, write it down, and flip everything else. 0, 1, 0, 0, 1, 1, 1. That's negative 27. Okay, 1, 1, 1, 0, 0, 1, 0, 1. And you could have done it the slower way by inverting all the bits and adding 1. I just think it's easier to do this. How about negative 127? Write down the 1, 1, 1, 1, 1, 1, 1, 0. That's negative 127. Or that's positive 127 now, negative to positive. And then 1, we already said that 1 is going to be all 1s. Okay? The easiest way to do this, again, write down a 1 and flip everything else. 1, 1, 1, 1, 1, 1, 1, negative 1. That's negative 1 in 2's complement notation. Negative 1 is all 1s. Okay? All right, so that's some practice. Now, let's talk about what happens in C when you try to convert between two numbers that are either signed to unsigned or unsigned to signed. Okay? Remember what casting is. Casting is saying, hey compiler, I know what I'm doing. Okay? It's saying, please treat this number the way I want it to be treated, not the way you think it should be treated based on its type. Okay? When you cast a number to another number that's signed or unsigned with the same number of bits, the underlying bits do not change. Okay? So what does that actually mean? Well, it means that when whatever bits you start with in the number, those bits actually remain. Okay? You can do this in either an explicit way, okay, where you just say, look, I'm going to put the cast in there, and I want, so tx and ty are signed integers, ux and ui in our case are unsigned integers, okay, and if I say tx equals parentheses int ux, I'm saying treat ux as a signed integer, and that's what the representation is going to be, or I could just do it. Okay, if you just say tx equals ux, well, the compiler says, oh, all right, well, I know that tx is a signed variable and ux is unsigned. I'm just going to take all the bits from ux and put them in tx, and that's it. Well, this actually has some interesting ramifications here. Okay, what this means is, well, first of all, it means that, guess what? You can't convert a signed number to its unsigned by casting. Okay? If you have a signed number, 5, and you turn it into if you have a negative 5, rather, that's that's signed and you try to convert it into a signed number, right, by casting, it does not become positive 5 because the bits are different. We already saw that on the number circle. Okay, it turns out the bits are very different. So what does that actually mean? Well, let's actually look at an example here. Okay, if we have a number here that is a signed integer, v, and it's negative 1, 2, 3, 4, 5. Okay, and then we say, all right, let's have an unsigned integer, uv, and then we'll do the actual cast for it. Okay, and let's print it out. Okay, we'll print it out as a signed value, and we'll also, and then this means the u means printed out as unsigned. Okay, let's see what happens. Okay, when we do this, we look and we say, oh, all right, well, the signed version is negative 1, 2, 3, or 5. The unsigned version is this big number that's near 4 billion. Why is that the case? All right, let's look at our number circle for the 4-bit again. Okay, remember 0 is up here and it's 0, 0, 0, 0. And we go all the way up to, we go all the way up to 7, which is 1, 1, 1, 1. Sorry, 0, 1, 1, 1. And then the next one is going to be negative 8, right? Oops, I did this on the wrong side here. This is 7. 7, 0, 0. This is negative 8, which is 1, 0, 0, 0, right? And this way we get 1, 1, 1, 1, and then down here we get 1, 1, 1, 0, and that's, I did it again on the wrong side, sorry about that. This is negative 1 and this is negative 2, okay, like this. What is our negative 1, 2, 3, 4, 5 in integer for? Well, first of all, it's a 32-bit circle, which we can't really draw very easily, okay? And what this means is this is somewhere down here. So let me just draw it like this. The negative 1, 2, 3, 4, 5, it's like somewhere up here. Negative 1, 2, 3, 4, 5. Why is it way up here? It's way up here because down here is like negative 2 billion, right? So it's way up here somewhere. How many ones are going to be in the number? A ton of ones are going to be in the number, right? Way up here. And when you convert that to a signed representation, let me just remind us what the signed circle, I don't think I ever showed you the signed circle. The signed circle is just this. It goes 0, and then this is going to be 8, right? It's just going to be like 0, 4, 7 is going to be here, 9, 10, right? And then 11, and then 12, 13, 14, 15, 13, 14, 15, like that, okay? That's how it works on the unsigned numbers. And what's the whole point about that? Well, numbers over in this range are going to be the biggest ones in the unsigned notation, and the small-ish negative ones are also going to be up here. So that's how the conversion actually works. Okay? What's the bottom line here? The bottom line is when I do this, when I say give me an unsigned int from a signed int, negative 1, 2, 3, or 5, the bits are the same. Okay? So the bits for negative 1, 2, 3, or 5 in signed int notation are the same as the bits for unsigned. So those numbers represent the same exact number of bits. Okay, so that's the key here, and I think the interesting part about it. All right, let's look at some examples of using printf here. Okay, if we say %d, that just means print a signed integer. Okay, really no matter what comes in the formatter, it will always treat it as a signed integer. If the compiler thinks that you're doing the number in the wrong format, it will warn you and it'll say, you know, %d expects a signed integer, but you're passing in an unsigned. Are you sure you want to do that? Sometimes you are sure. If you want to stop the warning, you actually explicitly cast it. But that's what it's going to give you there. %u will give you unsigned, and %x gives you the hexadecimal. In fact, it's the hexadecimal unsigned in there. Okay, so as long as it's a 32-bit type, printf will treat it according to the formatter. So if you say int x equals -1, and you say unsigned u equals 3 billion, okay, if you print out the unsigned and the signed notation, okay, for the same number for x, right? Well, for the unsigned notation, you're going to get a giant number, And for the signed notation, you're going to get -1 because it's signed. If you do the same thing here for the unsigned, you're going to get the unsigned version, 3 billion. And then for the signed version, you're going to get some like negative number that is probably, it's not going to be too negative, but in the range it's going to be. So let's actually see what happens here. Okay, we print out x, which is -1. And we say, okay, in unsigned, it's going to be this giant number here. I think I said that backwards when I did it. And in signed, it's going to be just -1. And for this one, we say, okay, the unsigned number is positive 3 billion. But if we try to print it in signed form, well, it just interprets the bits as a signed number, right? And this signed number happens, the first bit happens to be a 1, so it's going to be a negative number, and that's the negative number that is represented. Okay? You can play around with this on the code. In fact, I'll post the code in Lecture 3, samples/Lecture 3 under the website, or under the class directory on Myth, and you can actually see that. Okay, but the whole point is, when you do casting, and this is doing a cast just by saying, okay, printf's expecting a signed or an unsigned, it's doing a cast explicitly or implicitly, and it treats it in that form. The bits are exactly the same. That's the takeaway here. Okay. All right. So here's our two number wheels. I kind of showed you. I just briefly showed you the unsigned one. The signed one we talked about here. This is 2's complement. Okay. Unsigned, not 2's complement. It just goes 0 all the way up to 15 for the 4-bit numbers. Okay. And they're just the binary representations there. Okay. You should get very familiar with these number circles. Don't get too familiar with them thinking that all numbers are only 4 bits. Whatever bit width you have has its own associated circle, and that circle represents all the bits. So if you had an 8-bit one, it would go 0 all the way to 255, and you'd need 255 little hashes here for that one. Okay, but this is a very good way of thinking about it. All right, now here's where it gets a little bit strange. You can compare numbers between signed and unsigned. And by the way, if we give a constant number, if we just say 0, okay, 0 means a signed number. If you say 0u, you're telling the compiler, I want you to treat it as unsigned. Okay, so if you don't put a u on there, it means signed. If you do put a u, it means unsigned. Okay, so let's actually look at this. Here's how comparisons between signed and unsigned numbers go. First of all, you probably shouldn't do this unless you know what you're doing. If you're going to compare signed to unsigned numbers, you have to understand what we're about to talk about. If you keep from comparing, if you always compare signed to signed and unsigned to unsigned, then you'll get answers that make sense because they'll just be the comparisons you normally think of. But if you do comparisons between signed and unsigned, here's how it works. C implicitly casts the signed one to unsigned. So in other words, here's a comparison. 0 compared to 0u is signed versus unsigned. It treats them both as unsigned. Okay, so it says, all right, fine, this is 0 unsigned and 0. Now, we know that 0 unsigned and 0 signed is the same for both, right? But same bit representation. But in this case, -1 and 0u, well, it's going to compare them both as signed numbers. I'm sorry, unsigned numbers. Why unsigned? Because it always converts it. So it says this is -1 in sign. It's pretending it's unsigned. Well, -1 unsigned is actually all ones, right? So it's going to do that comparison. So it's going to treat this as a really big number, as it turns out, in the comparison. Okay, let's actually go through some of these. All right, 0 equals 00u. Well, unsigned 0 indeed is equal to 00. So it treats this as an unsigned number. Oh, here they all are. Treats this as an unsigned number, okay, because it treats both of them as unsigned. It does the comparison as unsigned, and it evaluates to true in this case. Okay, true is 1, 0 is false in this case. So is 0 equal to 0u? True. Okay, now here's an interesting one. Okay, -1 is less than 0. -1 is a signed number and 0 is a signed number. So in signed notation, is -1 less than 0? it is, because -1 is actually less than 0. So it's a signed comparison, and that is true. All right, let's look at this one. -1 is less than 0u. The compiler now says, I'm going to do this comparison in unsigned numbers. I'm going to think of -1 as unsigned. Okay? So if -1 was unsigned, remember, -1 is 1, 1, 1, 1. And if this was signed, this would be 0, 1, 2, 3. This would be down here, would be 8, and then 9, and then 10, 11, 12, 13, 14, 15. Okay? And it says, is 15 less than 0? No. So the answer is false. That's what's happening here. When the compiler says -1 versus 0u, it says, oh, I'd better treat this as both of them as unsigned, and therefore I'm going to say 15 is less than 0. No, that's not true. 0. Okay? Let's do this one. 2, 1, 4, 7, 4, 8, 3, 6, 4, 7. Signed number is greater than negative to the negative -1. Well, let's see what happens with this. Okay? Is this greater than this -1? Well, this -1 happens to be 2, 1, 4, 7, 4, 8, 3, 6, 4, 8. Okay? And so yes, this number is greater than this number. All right? So it's a signed calculation, and it's true. Okay? We haven't talked about what happens when we get past the, what happens when we do this thing called overflow. We'll get there in a few minutes. All right. Big unsigned number, is that greater than this number here? Well, this number we said was -214. It's basically, okay, saying now it's going to do this as an unsigned number. Well, this number in unsigned is actually way down here on the number circle. Okay, that's the number on the number circle, right? And it's saying, is this number greater than this number? Well, when you do them as unsigned, it's not. This number is going to be, in signed, it's going to be a very big signed number, unsigned number, and therefore this number is going to actually not be bigger than this one once it gets converted to signed, so that's false. Okay? All right, I'm going to clear some of this so that it gets, so we can see it a little better. How about this one? 2, 1, 4, 7. This is a what? This is an assigned number. This is an unsigned number. We just cast it to a signed number. And if you cast this to a signed number, it becomes signed. So you do a signed comparison once you cast it. Okay, well, this number signed is actually what? The problem is you don't necessarily know these numbers. You'll start to get these numbers. But this is exactly like saying, what if we cast +8 to a signed number? It becomes -8. And so is this number bigger than this number when this one is signed? Yes, it is. Whew. Okay. Let's look at another one here. Let's look at -1 is greater than -2. They're both signed numbers. -1 is greater than -2. That is true, because they're both signed numbers. Okay? If we then convert this one to -1, or to a unsigned number, well, let's look at what happens. This unsigned -1, right, that becomes this number, and if we did it in 4-bit numbers, this would actually be 15. Is 15 greater than -2, which is also going to be converted to unsigned, because if one comparison is unsigned, the other one has to be unsigned. So this is going to be 1110, which is 14. Is 15 greater than 14? That is an unsigned comparison, and it's true. Okay, now that was a lot of stuff all at once that might be a little confusing. The good news is most of the time you won't be doing these comparisons, because you'll know it's probably not a great idea to compare signed and unsigned numbers, but at least you understand how it's done. Okay? Spend some time figuring out what this is. Put some questions on Piazza if this doesn't make sense. Okay, let's try this in a little more abstract way. Okay, if that last one didn't work for you because of the actual numbers, let's just think about this in a little bit more abstract way. The number line, and I've abstracted it here, this number, it's going to be all zeros right up the top here. And then remember, it goes down here, it actually is the crossover point for if it's signed, down here it goes from being a positive number to a negative number. If it's unsigned, it's all the way positives all the way up. Okay? So let's actually look at this. How many of these statements are true? All right. S3 is greater than U3. Okay. S meaning signed, U meaning unsigned. Okay? So we've defined them that way. All right. Is S3 greater than U3? Well, let's look. S3 is going to be here on the number line, signed. U3 is going to be here. They're both considered unsigned because it's an unsigned comparison because one of them is unsigned. So therefore, is S3 greater than U3? Certainly it is. Okay, so that's positive. That's true. Okay, let's say, we've got them all in here. I'll just leave that one's true. Okay, let's look at U2 versus U4. All right, well, U2 is over here on the number line, and U4 is over here. And if we're talking about unsigned comparisons, remember the unsigned numbers just go, get bigger, 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 all the way up to the biggest unsigned number up here. So is U2 greater than U4? Sure it is. Okay, it's bigger on the number line. Okay, let's look at S2 greater than S4. S2 is over here and S4 is over here. If they're signed numbers and it's a signed comparison, well, once we cross over here, we get into the negative numbers. Is this number greater than this number if this is a negative number and this is a positive number? No. Okay, so S2 is not greater than S4. Okay, so that's false. How about S1 greater than S2? Well, let's look. S1 versus S2. Remember, the numbers, this is the least negative, or the most negative number down here, and it goes less negative as we go up here. Remember, this is -1, -2, -3, -1, -2, -3, -4, etc. Okay? So is S1 greater than S2? Sure it is, because S1, they're a signed comparison, signed and signed, and this negative number is less negative than this one, so S1 is greater than S2. We are true. Okay? All right, let's look at U1 versus U2. All right, is U1 greater than U2? Sure it is. Unsigned are easy. Unsigned just continually get bigger, and therefore U1 is greater than U2. True. Okay? Let's look at the last interesting one here. S1, is it greater than U3? All right. S1 greater than U3. Now, if it was a signed comparison, we would know that S1 is negative, right? And that's the signed number S1 is negative. But when you do the comparison between a signed number and an unsigned number, you compare them both as if they were unsigned. And therefore, we say, okay, is this number greater than this number if we're thinking of them as unsigned? Yes, because unsigned numbers continually get bigger this way. So S1 is greater than U3, even though S1 is a negative number on the signed sense. Okay? All right. Again, that's a lot of stuff all at once. Pause the tape, pause it, and see what, retry it, look through it, ask questions on Piazza if you're still confused about this. All right. Let's go through some more C issues here. Okay? In C, we have this thing called the size of operator. Okay? Size of tells you the size in number of bytes of a variable or a type, and you can apply it on either. Okay? What it does is it says, all right, look, if I say size of char, that's going to be 1 because a char is 1 byte long. In fact, it's defined that way in C, for what it's worth. Okay? If we do size of shorts in C are actually, on the myth machines anyway, are 2 bytes. So that's going to be 2 bytes. Okay? Size of int, 4 bytes. Size of unsigned int, also 4 bytes. Okay? And because unsigned ints and ints are both the same width. Okay? Size of longs, turns out that's 8 bytes long. Okay? Size of a long, actually, I believe that's actually a also 8, as it turns out, on our machines. Okay, a size t. Okay, I briefly mentioned size t. What size t is it's this type that says, okay, it's big enough to hold any pointer on whatever machine it is. We've already said that pointers are 8 bytes long, so a size t on the MITH machines happens to be 8 bytes long. Okay, pointers, a size of a void pointer, also 8 bytes long. Okay, pointers are always on the MITH machines 8 bytes long. Now, what does this mean? Size of is interesting in that it is an operator actually, and it happens at compile time. So as long as the compiler can figure out how big a type is at compile time, and it always can the way C works, then it actually just puts that number in, and it doesn't happen when the calculation is happening in runtime, okay? But it's useful. Now, it will become useful. Right now, we've never needed to use this in any other programming course because we never needed to worry about the idea of, well, what if we don't know how long these numbers are? What if we don't know how big they are? This will eventually, in a couple weeks, become very, very useful to us. Okay, let's talk about the minimums and maximums a little more explicitly for some of these number types that we're talking about. Okay, so when we talk about signed numbers, okay, signed numbers are going to go from, remember on the number circle we had the signed numbers. It was for the 4-bit ones, we went 0, 0, 0, 0 all the way up to 1, 1, 1, 1, and this was -1, and down here we had 1, 0, 0, 0, which was -8. Okay, so if we have 4-bit numbers, right, we can only represent up to 2 to the third. Negative 2 to the third is the minimum we can represent, right? So what it is it's -2 to the number of bits minus 1. Okay, that's how the minimum value is going to be. Okay, for the maximum value, we can represent up to 2 to the width minus 1 minus 1 because we've got that odd number in there that we can represent. Okay, so in this case it goes, for our 4-bit one, it goes 0 all the way up to 7, right? And it goes 0 all the way down to -8. Well, 0 up to 7 is 2 to the number of bits, which is 4, 2 to the 3, which is 8, minus 1. We can represent up to that. Okay, so let's look at a couple of these in here. And we've actually done them in hex as well as in the number of width in bytes and bits. Okay, so for chars, which are a signed type, okay, 8 in hexadecimal is 1000, and then we have 0 in hexadecimal is 0000, okay, and this is the minimum number for a hex in, or a minimum number for a char, or for a signed char, okay. 80 is the minimum. Okay, how do we know it's negative? Because it starts with a 1, and it's the minimum because it's all zeros, and on that number line, the one down here is 1 with all zeros. Okay, so that's the minimum there. Okay, this happens to be -128. Okay, and then the maximum is 7f, and 7 in hex is 0111, and then f is 1111. All right, we know it's positive because it starts with a 0. And it's the greatest positive number here. And in this case, it's going to be the number positive 127. Okay? Notice something here that in parentheses here, I put this uppercase value here. This is a constant value defined in C. So if you want to know what char min is and you don't want to figure it out, you can just use char underscore min and it tells you that. The one that we're going to use more often are int min. There's also the maximum ones, int max, and there is the maximum unsigned as well. Okay, so in this case, let's look at int min for a minute. Int min goes, it's 4 bytes long, 32 bits, meaning that this number is going to be -2 to the 31. That number, if you figure it out, -2 to the 31. So what we've said here is that we have an int, which is 4 bytes long, 32 bits, which means the negative is going to be negative 2 to the 31, which we can actually do in Spotlight on a Mac. If we do negative 2 to the 31, it will tell us that the value is 2147483648. That's the minimum value of an int, negative 2 raised to 31 power. Okay, all right. Let's look at the and by the way, remember this is just 1, 0, 0, 0, and then all zeros, 32 bits long. Okay, 7FFFF is going to be 0, 1, 1, 1, and then all ones for the rest of it here. Okay, this is actually going to be 2 raised to the 31 minus 1. And we can check that in Spotlight by doing 2 raised to the 31 minus 1. It gives you 21474834647, and that is the maximum number for integers on the MIT computers. Okay, so don't stress too much about this. Know that you can get the values by doing int min and int max, and uint min, or uint min doesn't exist because it's just 0, but uint max gives you the the maximum number for an unsigned integer. Okay, let's actually do that one in. By the way, that should be 2 raised to the 32 minus 1, because it can go all the way from 0 up to that number. And let's actually look at that in Spotlight as well. That's going to be 2 raised to the 32 minus 1, which is 4,294,967,295. Okay, so again, the takeaways for this are you can use these constants to get your values. You should know how they look. Okay, you should know that the lowest value in a signed number is going to be 1 followed by all zeros. You should know that the greatest number should be 0 followed by all ones. Okay, you should know that for an unsigned number, the lowest is just going to be all zeros, and you should know that the highest is going to be all ones. Okay, negative 1 again is going to be all ones for a signed number. So those are the kinds of things that you should recognize when we're talking about integers and mins and maxes. Okay, let's say we are doing some more casting here. Okay, let's say we want to convert between two integers having different sizes. In other words, let's say we want to convert a short to an int or an int to a long. Well, first things first, if you go from a long to an int, you might lose some information. Why might you lose some information? Because you can't fit all the longs into the range of all the ints. It just doesn't make any sense. Okay, so there are long numbers that are bigger than we can fit in int. So we're going to lose some information there. You can always, however, go from a smaller type to a bigger type, and let's see how that actually happens. Okay, for unsigned values, it's easy. Okay, you start with the number of bits in the unsigned value for the smaller value, and you just add zeros to make up for all the digits that are not represented in the smaller width number. So if we convert a short 4, which is a 2-byte number, into the 4-byte or 32-bit int, we have the same bits in the lower 16 bits, and the upper 16 bits are just zeros. Straightforward. Okay. All right, well, what happens, okay, for a signed number? That was for unsigned numbers. Now for signed numbers, we've got a little, an interesting thing going on here, okay? Remember how when we talked about shifting, we had those two weird shifts where we said one shift is shifts in all ones if we're going to the right, and shifts in all zero if it's a signed number and the high bit is 1, it shifts in ones. If the high bit is 0, it shifts in zeros. This is the same kind of idea here. Okay, you extend, in other words, you make all the remaining bits that upper bit. So a signed 16-bit number, that upper bit, if it's a 0, it means it's a positive number. So when we convert a the 4 from signed short to a signed integer, okay, it ends up just taking that number, making it zeros, the bottom 16 bits are the same, and the upper 16 bits are now zeros. But what if the number is -4? It actually sign extends it. In other words, it takes the bit at the upper bit and it says, if I'm going from a signed number that's negative to a bigger width that's also signed, I am going to convert it and say, okay, fine, I need to now take that sign bit and make all the upper bits that same sign bit. So if it's a 1, it's going to become 1s. Now, how does this work out? Well, it works out because on the number circle, right, remember like -1 is up there and it's all 1s, 1, 1, 1, 1, right? Well, if we just made this an 8-bit number, right, well, -1 here is going to be 1, 2, 3, 4, 5, 6, 7, 8. The upper bits are all going to be 1s. In fact, for an 8-bit number, all the numbers on this side have the first 4 bits, 1, 1, 1, 1, right? And then, I'm sorry, all have the upper 1, 0, 1 with the number there. But if it's a number that fits in the range of the smaller number, it is going to have all the upper bits 1. Okay? So the numbers that fit in there are going to be that. So what's the takeaway on this? The takeaway is, if you're going from a smaller signed number to a larger signed number, you take that upper bit and you say, oh, I'm going to make that bit all the bits for the larger number for signed. Okay? That's what's happening there. Play around with that a little bit. Again, ask questions on Piazza if it's still a little confusing. Okay? Here's an example of how this works in C. If we have a short, remember that's a 16-bit number, -1, 2, 3, 4, 5, okay? And we then cast it to an unsigned short. Remember, casting does not change the bits. So the bits here, -1, 2, 3, or 5, are the same bits as 5, 3, 1, 9, 1. -1, 2, 3, 5, and 5, 3, 9 have the same bits in them, okay? If we now say that we say, let's take the signed 16-bit number and make it a signed 32-bit number, well, it extends the bits, and so it is indeed -1, 2, 3, 4, 5, but it's got a whole bunch of 1 bits ahead of the number that was the 16-bit version. If we then cast this 32-bit int, signed int to a 32-bit unsigned int, we end up with a same bits, right? And it converts it by considering it as a positive number. Okay. So let's actually look at the what's happening here. And this is probably not the best idea for me to do, but when we have this have a program. This program, by the way, there's a show bytes function that's actually in your textbook. Show bytes will show the bytes in little endian format. Remember, it's going to be the little end is going to come first, meaning the last bytes are going to be the higher order bits of the number, the most significant bits. Okay, if we take a signed number and we convert it to the unsigned version of the same width, okay, it's got exactly the same bytes associated with it. If we take the number and convert it to an signed version that is more bytes, well, now we've got twice as many bytes in this case because a short has 16 bits and a int has 32 bits. What do? We put FFFF, which is all 1s, which is the high order bytes of the value, all 1s, okay? And then when we when we convert that number to, let's see, when we convert this number to a signed version, I believe, let's see, signed, oh, right. What was happening over here was we were saying, okay, let's do the conversion from our signed, unsigned short to our signed short, okay? Well, to our unsigned short. Unsigned to unsigned just puts zeros in there, so we get zeros as the upper bytes. Okay. This is definitely can get a little bit confusing. Look at the code posted online, try it out, run it in GDB, and see what happens. Okay? So back to the shifting again. When you do right shift, we said that the value behaves differently for signed and unsigned numbers. Well, why is that the case? It's the case because we want to keep the sign properly. Okay? So when we do a right shift, we want to take the number and keep it as a signed number if it is already signed. Okay? What does that actually mean? Well, it means that it keeps the number, if the number is signed and has the highest bit being 1, the right shift ends up shifting in ones as it shifts it to the right. Okay? So let's actually look at this right here. If we have a number 1048567, okay, and that is a positive number, okay, the positive number, well, it's going to have its high bit being a 0, so when it gets shifted by 8, all the bits that get shifted in are zeros. Okay, you actually shift in 8 zeros as it turns out. Okay, if we have B being a negative number, well, the highest bit is a 1. We're not necessarily sure unless we go figure it out. The highest bit is a 1, but what it does is when you shift 8, it shifts in 1, 2, 3, 4, 5, 6, 7, 8 ones when it does the shifting. Why? Because that's going to keep it as a negative number. And that's what we want to do. We want to when we shift numbers, we don't want to change the sign on them. We just want to shift the bits over. Well, it has to do that in the way that keeps it negative because we have this 2's complement notation. Okay? All right. Again, I've done this right shift with the little endian machine here. And so what's happening is a positive number, it shifts to the right, meaning that this 1, 0 shifts down to this byte. We shift in zeros. If it's negative, we shift the F0 down to this byte, and we shift in FF. Okay, we shift in 2 zeros up here, FF down here. Okay. Again, this is like low-level details here of what's happening, but it all goes back to understanding that, hey, when we're dealing with 2's complement numbers, negative numbers begin with a 1 in the most significant bit, and they end, and when you're doing the shifting, we want to keep them as negative numbers, so we have to keep shifting in ones to keep them negative. Okay, a couple more things. When we truncate numbers, okay, if we want to reduce the number of bits, in other words, if we want to go from an int to a short, well, we may lose some information. It turns out that 53191 is too big to fit in 16 bits. Okay, 53191 is this. It is that number right there. Okay, so what's happening? Well, if we get rid of the high order bits, luckily they were all zeros anyway, so that actually is the first good thing. But the thing that has a problem here is now look, when we convert this number to a 16-bit number here, when it's now 16 bits, well, guess what? That high bit is 1, meaning it's going to be a negative number. 53191 is too big to fit in the 16-bit number. Remember, for signed a 16-bit signed number, remember, for a 16-bit signed number, we can only go up to 2 to the 15 minus 1. Let's see what that number actually is if we go into Spotlight. 2 to the 15 minus 1. We can only represent up to 32,767. Well, guess what? We've got a problem here, right? We have a problem in that this number is too big. It's bigger than the 32,767 in there. It's too big. So this number, when we convert it from a 32-bit int into a 16-bit short, we're going to lose that information. Okay, this is actually a form of overflow, as it turns out. I mean, it's basically saying we've tried to convert a number that's too big into a representation that can't fit that. So what happens? It turns it into a negative number and ends up being that negative 1, 2, 3, 4, 5 that we saw before. Why? Because the highest bit is the sign, and the rest of this is the 2's complement notation for the negative, the 1, 2, 3, 4, 5. Okay, this whole number is the 2's complement notation for negative 1, 2, 3, 4, 5. So that's a problem when you're trying to do truncation. You have to make sure that if you're going to truncate a number by casting it to a smaller size, that it fits. Okay, and that means that we would have to have had a number up here that's less than 32,767, but we didn't. We tried to do it, and it turned into a negative number when we converted it. Okay, so again, this is a sign of overflow, and we don't have enough bits to store this. Okay, you can play around with this, by the way. If you go to here and you go to this 2's complement calculator, you can actually play around with it and see some interesting examples of this. Okay. All right. If the number does fit in the smaller representation, it will convert just fine. So negative 3 in 32-bit form looks like this. Why are there all these zeros and ones here? Because it's negative 3, and the only ones that really, that 101 is the negative 3. If we looked at a number circle, right, we'd get 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 0, and then negative 3 would be 1, 1, 0, 1, right? And that 1101 is the negative part. For a 32-bit number, it's all ones all the way up to that 1101, which is the negative 3. So when we do the conversion here, does negative 3 fit into 16 bits? Sure, negative 3 fits into 16 bits. Okay, so what you do is it truncates just fine. Those bits also represent negative 3 in 16-bit. Why? Because it's all ones and then 1101, which is negative 3. So that actually works just fine. Okay, again, play around with it down here. Okay, all right. We can lose information with unsigned numbers. Why can we lose information with unsigned numbers? Well, because again, we've only got a certain range here. So let's take a look at the range here for 128,000. Now, 2 to the what? 16 minus 1 is our maximum unsigned short. Okay, so if we do that and we check what that is, 2 to the 16 minus 1, we can represent up to 65535. Okay, 65535, which is our maximum. Okay, 65535 is our maximum. Well, guess what? We're trying to convert an int, which is 128,000, into a short, which can only hold up to 65535. What happens when you do that? Well, there's your number that results. All of this gets truncated away, and that information with that 1 is gone. Now we've got this number, which in 16-bit unsigned format is actually 62464. Right? So it did not convert it. Now, what were you really expecting? Trying to convert 128,000 into a number that can only hold up to 65535. You're going to get some number that is less than 65535 by definition. Turns out that it's that number, but it's not any, like, you can't really say, oh, well, it's some sort of number related to this. It is, but it's not something we care about, right? So you've lost information. You've overflowed the 16-bit number. Okay? Now, what happens when we do addition and overflow? Okay, well, guess what? We already said, remember we talked about the fact that this was the biggest number that you can hold in an int? If you, and in fact we've called it that right here, we've said that it's an uint max. If we add 1 to the uint max, what happens? Well, we add up all, we start with all ones, and then we add 1 to it, and if you add to 1, let's say our 4-bit example, let's say this was our 15 on the number circle here, 15, if we were using 4-bit numbers. We add 1 to that, well, we get 1 plus 1 is 0, 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 and then the 1 over there, but we can only count those 4 bits, it turns into zeros. What happens is when you add numbers that go outside the range, they wrap around and overflow, okay? And we actually don't call them overflowing when they're unsigned. We say that it wraps, and that's just the way it works. Okay, if you were to add 2 numbers that end up bigger than this number and they're both unsigned, it wraps around to the other side and you end up with possibly a small number. Okay, how do you test that? You can look at a little code here to see how to test that if you want. Okay, all right, well, let's see. So that's for unsigned addition. What happens when we try signed addition? Turns out it wraps, but it wraps to negative numbers, right? Because here's where it wraps, by the way, on the number circle, right? Let me redraw that. If you have a number circle here, right, remember it goes 0 and then 7 is here, and this is -8. That's where it wraps. It wraps when you add two numbers together. So if you tried to add 6 plus 7, right, it would wrap there. Or in fact, if you had to try to add 7 plus 1, it would end up being, because remember, 7 plus 1, 0, 1, 1, 1, plus 1 gives you 0, 1, 0, 1, 0, 1, 1. 1, 0, 0, 0 in signed integers is -8. This actually manifested itself, interestingly, with the Gangnam Style video on YouTube. Somebody at YouTube used signed integers for the counter. They probably thought that no video would ever get more than 2 billion views. And so they said, well, we'll just use a signed int. So for a while, once Gangnam Style got more than 2 billion, more than int max number of views, it wrapped around to negative numbers, and it said that Gangnam Style actually had -2 billion views, right? So that's what happened. They used int max. Okay, now, that's what happens when you do signed overflow. Technically, signed integers, when they overflow, is actually undefined. It's part of the C standard that says if you overflow a signed number, we do not guarantee that you get this wrapping behavior. You can do it however you want. The compilers can do whatever they want. Why is that the case? Well, some compilers, some machines don't use 2's complement, so they use some other method, and that's the way it is. If you want to check if signed integers is going to overflow, you can use this little code here, which will actually do the check for you, and it says, look, if x is greater than 0 and a is greater than int max minus x, when you add them together, you will get a number that's bigger than int max, and it will wrap around. Okay, so for most machines these days, you can see that the behavior is this wrapping that we talked about, the Gangnam Style wrapping like that. But if not, but you can't actually base your program on that for any compiler because it's undefined in the C standard. Okay, that was a lot of stuff for this lecture. The big takeaways are that signed and unsigned numbers are different in their bits. Okay, signed numbers have this 2's complement notation. Unsigned numbers are just the bits in regular old binary notation. You should know how to convert between signed. You should know how to convert from a signed positive number to a signed negative number using the 2's complement conversion. You should understand that addition and multiplication and subtraction are all very easy with 2's complement numbers. You should understand how to compare unsigned and signed numbers, and you should understand that you've got these maximums down here as well. All right, that's the lecture, and put some questions on Piazza or email me if you don't understand some things. Thanks.